Hey everyone, today we're going to finish out section 5.3. If you remember, we have been talking about the atomic emission spectrum and the quantum mechanical model. We've been talking about evidence that supports this model and that supports what we see in our atomic emission spectrum. And today we're going to learn how the ideas that support these models can be used in other areas of science. So let's go ahead and get started. So if you remember where we left off, we talked about Max Planck, and he is a scientist who explained the relationship between energy that an electron absorbs and releases and related it to the frequency or wavelength of light that we saw. Remember, energy and frequency are directly proportional, so that means as the amount of energy an electron absorbs and releases increases, so does the frequency of light. Now, other scientists actually used Planck's quantum theory to explain other areas and other things that we saw in science. And one of these things is the photoelectric effect. Einstein used Planck's quantum theory to explain this. What is the photoelectric effect? Well, it's when electrons are ejected when light shines on a metal. Now, not just any frequency, or in other words, color or wavelength of light, will cause the photoelectric effect. For example, if we look at potassium, which is a metal, we will see that red light will actually not cause electrons to be ejected. It does not matter how intense or bright that red light is, it will not cause potassium to lose an electron. But if I shine a very weak yellow light on potassium, we will see the photoelectric effect take place. Now, why do the different colors of light matter? Well, remember, if we think back to this diagram, this has our visible light spectrum. Note that red light has very low energy, whereas yellow light has about a little bit of medium energy there. So what this is saying is that red light did not have enough energy to pull that electron away, but yellow light does have enough energy for that electron to leave potassium. So one thing to note about this photoelectric effect is that it didn't explain this concept using classical physics. Now, classical physics is going to be large objects, and we'll actually define this later in your notes. But when we're talking about anything bigger than an atom, such as a person, a baseball, a marble, we use something called classical physics to describe the motion and energy within that object. But classical physics didn't completely explain this effect. However, it did describe light as a form of energy. But classical physics tells us that under any light, whether it was weak or strong, eventually that electron should gain enough energy to be ejected. And we didn't see that. What we saw is under red light, it just didn't happen. So why did it not happen? We had to think of a new way and a new explanation and new support to explain this. And so the idea of quantum physics came into play. So our key question says, how did Einstein explain the photoelectric effect? To explain the photoelectric effect, Einstein proposed that light could be described as quanta of energy that behave as if they were particles. Now, quanta is just packets of energy, and one thing to know about light and energy is that they are not considered matter. So how do they behave as if they are matter? Well, we call these light quanta photons. And Einstein's theory is that light behaves as the stream of particles known as photons. And these photons happen in specific units or packets of energy. They don't happen as a range. So you can't keep building energy kind of like you would build temperature in a pot of water. They happen in discrete forms or discrete packets. So we can go from an electron from energy level 1 to energy level 2, but we can't hit any in between levels. We can't hit a 1.5. So, with this understanding, we now know that light behaves as waves, like we've learned in the past couple lessons, but we also have to consider that they also act as particles in other situations. So we say that light has both wave-like and particle-like properties. So here's an image of the photoelectric effect that is included in your notes. Please note that mine is in color, so it would be kind of beneficial for you guys to write down the color that is in these images because it helps explain what we're seeing. In the first image, we see a red light. Note that the red light has a big wavelength, which means it has a low frequency, and that means it has pretty low energy. So these electrons are not going to be ejected because the energy or frequency of the light is below the amount of energy needed to eject it. In the second image, I see a green light. Now, a green light is in the middle of my visible light spectrum, so it has about that middle frequency, and so it has about medium energy. This color light has enough energy to cause that electron to be ejected. And then if you keep going over on that visible light spectrum, we'll see this violet or indigo. This has a high frequency, so this also has high energy. Not only does indigo or violet light in this image have enough energy to cause that electron to leave, but note that the even higher energy caused that electron to move faster. Now, with this idea, we have brought about the idea of quantum mechanics. It applies something called quantum physics. Given that light can behave as waves and particles, why can't particles of matter, such as humans or baseballs, behave as waves? Why don't we see that? Well, this was investigated by a scientist named Louis de Broglie, and he referred to the wave-like behavior of particles as matter waves. And these do exist. He created a mathematical expression for the wavelength of a moving particle. So when we say moving particle, we're talking about things like people, but also things like atoms. And in fact, today we use this wave-like properties of matter to explain and use in everyday life. For example, the wave-like property of electrons are useful in viewing objects that cannot be viewed with an optical microscope. And when I say optical microscope, I'm talking about something like a light microscope that you might see in a biology lab. If you were to take a grain of pollen and look at it underneath a light microscope, you would see kind of just circles. But electrons in something called an electron microscope, these have much smaller wavelengths than visible light. So these smaller wavelengths actually allow us to take an image of pollen and enlarge it, but also make it a lot more clear so we can see more detail. So if I look underneath a normal microscope, this would just be a blob of a circle, but under an electron microscope, we can see all the edges and points of this pollen grain. If you're in biology, you might be like, how do people understand the shape of viruses? How do we know they have these shapes? And again, we look at it through quantum mechanics and this concept. So how does quantum mechanics, or in other words, quantum physics, differ from classical mechanics or classical physics? Well, one thing to know is classical physics describes anything that is larger than atoms, but quantum mechanics describes subatomic particles or anything smaller than atoms. And they describe them and they give ideas of how they act as waves, but also as particles. Now, this brings up our last point that we're going to talk about in this section, and it's called the Heisenberg uncertainty principle. This principle states that it is impossible to know both the velocity And if you've taken integrated science, velocity is the speed of an electron and the position, in other words, the location of a particle or electron at the same time. Now, this limitation of not knowing speed and location only is critical when we're dealing with something so small like electrons. This does not apply and does not matter for things like cars, people, or airplanes. Now, why, if you are smaller than an electron, does this uncertainty principle come into play? Again, it has to do with the size. To even locate an electron, we have to strike it with a photon. Remember, a photon is light energy. Now, an electron has such a small mass that striking it with this energy affects its motion, and it can cause it to move in a completely unpredictable direction and speed. And so the very act of figuring out where an electron is located changes its speed, making now its velocity uncertain and its location uncertain. So this image down below says before the collision, a photon strikes an electron to observe its position. But as soon as this photon hits this electron, it causes the electron's velocity to change and be uncertain. This idea of quantum uncertainty is illustrated in a thought experiment by Erwin Schrödinger, and it's called Schrödinger's cat experiment. Note that this is a thought experiment, which means he didn't actually do this. He said that we have to assume all quantum states exist at the same time until we can observe them. So, what I mean by quantum states is I mean location of electrons. So, we have to assume electrons can be anywhere in the atom outside of that nucleus at any given time. And it says, imagine a cat is put in a box with a lethal, which means deadly, radioactive source. We have to assume if we close that box, if we cannot observe it directly, we have to assume that that cat in the box is both alive and dead until we can actually see for ourselves and observe the situation. Unfortunately, we can't just observe things in electrons with our naked eye. We have to use indirect methods. So this suggests that we have to basically assume that an electron is in all possible locations in an electron cloud until we are able to determine its location. And then, of course, the moment we determine its location, it moves. So it's a never-ending guessing game. And that's the end of 5.3. If you have any questions, please make sure that you ask, and I hope you guys have a great day.